I hope you all are doing well today. Before we get started on today's lecture, does anybody have any questions or anything about the homeworks? All right, well, we'll go ahead and get going. So today we are going to talk about the various circuital laws that we are going to wind up applying throughout the duration of this course. We are going to start with Ohm's law. And in addition to Ohm's law, we are also going to talk about the concept of resistance and the roles that resistors play in circuits. So in a traditional engineering 221 class, you guys would have done a lab experiment at the end of the last class meeting. I'm going to describe that experiment to you guys. And this is an experiment that's actually very similar to how a German physicist named George Simon Ohm developed his relationship between voltage, current, and resistance. So let's say that we have a black box network. So what I mean by a black box network is simply some sort of electrical network where we aren't really sure what's inside of it. So it could be some combination of circuit elements. It could be a single circuit element. Doesn't particularly matter because we literally don't know what it is. Now, I'm going to make an assumption here that this is what's called a linear network. We're going to talk about the concept of linearity on next Monday's class meeting, if I've got my schedule right. But effectively, all it's going to mean in the context of what we're dealing with right now is that the components that are inside the black box do not change with time or temperature or things like that. Okay, so let's call this a linear black box network. And this network is a two-terminal network specifically. Now, realistically, it could have more terminals, but we are only able to determine what's called resistance by looking into a pair of terminals like I've drawn here. So we're only going to worry about a two-terminal network. So I'm going to connect to this linear black box network some type of excitation source. Now, this excitation source could be a voltage source, it could be a current source, it doesn't matter. I am just going to make the caveat in this case that it is a DC excitation source that's being used to energize our circuit. And if we were to measure the voltage drop across the terminals of our network, as well as the current flowing into the terminals of our network, we would observe that there is a constant of proportionality that relates the voltage and the current in this linear black box network. And that constant of proportionality is defined as the resistance. So resistance, R, is simply the ratio of the measured voltage drop across a network divided by the amount of current flowing into the network. And we're going to give the unit of resistance. We can very easily see that it's going to be 1 volt, which is the units of voltages, divided by 1 amp, which is the units of current. And we call this an ohm with a symbol of capital omega. Where let me make a note here really quickly that this R is resistance. Now, realistically, we could observe a second constant of proportionality between our voltage and current quantities. Okay, so we're going to call this one G, where G is representative of the conductance. And the conductance is simply the ratio of our measured current divided by voltage. And so in a DC circuit, this is nothing more than the reciprocal of our resistance. So from a units perspective, we have 1 amp per 1 volt, and we call this a Siemens, like the German electronics company. And Siemens has a symbolic representation of a capital letter S. And this G right here stands for conductance. All right, so resistance and conductance play incredibly similar roles. In fact, let's define them here really quickly, using words as opposed to mathematical relationship, okay? So we will define resistance as a measure of how difficult it is to pass a fixed amount of current through a medium. So for a medium with a large resistance, it means it takes a lot of work to pass current through it. And for a medium with a small resistance, it takes a little amount of work to pass current through it. Conductance, on the other hand, is going to have almost the exact same definition, except that we're going to say that conductance is a measure of how easily or how easy it is, excuse me, to pass a fixed amount of current through a medium. Okay. So let's talk a little bit about resistance, okay? So resistance depends on a couple of different things, okay? It depends on the material that we're trying to pass current through, but it also depends on the geometry of the material. So this is an equation that I believe you guys were introduced to in Engineering 121, at least back when I taught Engineering 121. It's something that we used. It's okay if you haven't seen it before. We're not really going to use it again in this class. I just want to illustrate something. So resistance R can be expressed as rho sub E times length divided by cross-sectional area. Okay. So let me write this out. So where rho sub E is the resistivity of a material, L is the length of the material, and A is the cross-sectional area of the material. So let's consider a section of wire. Okay. So let's say that I have a wire and it's going to have a circular cross section where the diameter of this wire is 1.024 millimeters. This would correspond to AWG, or American wire gauge number 18 wire, which is very similar to the wire that you guys used to connect things in your circuits in your engineering 120 series class. And let's say that this wire has an overall length measured from here to here of 10 meters. So let me ask you guys a pretty straightforward question, I hope. How does the length of 10 meters compare to the length of wires that you've used to connect your circuits together previously?
It's very long.
It's a lot longer. It's about 30.
Much longer.
Yeah, so 10 meters is going to be, I think, around 31, 32 feet. So it should be significantly longer than the lengths of wires that you guys have used previously. Okay. Let's say that our wire is made of solid core copper, and copper has an electrical resistivity, rho E, of 1.68 times 10 to the negative 8 ohm meters. And I want us to determine the resistance of this section of wire. Okay. So for this AWG number 18 wire, our resistance would be our rho E, so 1.68 times 10 to the negative 8 ohm meters, times our length of 10 meters, divided by our cross-sectional area. So whenever we have a diameter, it's going to look like pi times the diameter squared over 4. So that's going to be pi over 4 times our diameter, which is 1.024 times 10 to the minus 3 meters squared. And if we put this in our calculator, I believe we will get a result of 0.204 ohms. Okay. So let me ask you guys another question. How does this resistance of 0.204 ohms or 204 milliohms compare to the size of the resistances that you've used when constructing circuits.
It's not
Very
much.
small.
Much, much smaller, right? So also, just a couple of things here. The length of this wire is 10 meters, or roughly 31, 32 feet. If our wire was only a couple of inches long, do you think this resistance would be larger or smaller than its current value of 204 milliohms?
A lot smaller.
It'd be a lot smaller, okay? So for the intents and purposes of this class, anytime we're dealing with a wire, we are going to assume that it is a perfect conductor of electricity and therefore has zero resistance, okay? So that's going to bring me to my next little thing here, which is what we're going to call short circuits and open circuits. And these rules for how these behave are completely just pulled from Ohm's law, okay? So a short circuit, we are going to consider to be just a section of wire where, based on our prior analysis here, we could say that the resistance of a section of wire, as long as it is not too incredibly long or too incredibly small in cross-sectional area, should be about 0 ohms. So according to Ohm's law, then, the voltage drop across any short circuit or just section of wire that we see is always going to be considered to be 0 volts. Okay? So anytime we have just a section of wire, we are going to say that there's no voltage drop across it. That's exactly the reason why we got to treat effectively all points that are connected to each other between two circuit elements as the same node on the first day of class. Okay. In an open circuit, we're going to have something like this. So effectively what we've got here is an absence of wire. Okay. The resistance of an open circuit is going to be assumed to be infinitely large. And that means that no current will ever be able to flow through an open circuit. Now, both of these are approximations, okay? So we literally, not even 5 minutes ago, figured out that actual wire does have some amount of resistance. It is typically very small, and so that's why we are going to be neglecting it in this class, because it's going to be very small in comparison to the size of the resistors that we're going to be dealing with, so it's not really going to contribute much of anything. But that resistance in a real section of wire absolutely exists, and when we get to some of our more esoteric topics, we're going to bring that back to kind of explain why things happen the way that they happen. With regards to an open circuit, well, really, it's just got a very, very large resistance. It isn't infinitely large, right? Some of you have probably seen sparks and stuff like that come out of outlets when you plug things in or unplug things. And that's because if the potential difference is high enough or the voltage is high enough, we can make current flow through air, okay? It depends on what's called the dielectric breakdown voltage of the medium. So if we are able to establish a large enough electric field, again, not really important for this intents and purposes of this class, just explaining what's going on. But if we were able to establish a large enough electric field, we can cause current to flow through effectively nothing at all. That's exactly how lightning strikes and all of that kind of stuff conduct electricity from the sky down to the earth. the electric field strength is so large that it literally ionizes the air particles and creates a conductive path. So we have these two idealized cases of short circuits and open circuits, and then every practical resistance lies somewhere in between these two extremes. Okay. Let's see. So let's talk very briefly about what a resistor does. Okay, and this is really all a resistor can ever do. Okay, resistors exist effectively to convert electrical energy into heat. Resistors, and by extension conductances or conductors, just because they're the inverse of resistors, can never store any amount of energy. All they can do is heat up. If we apply electrical energy to a resistor, it is going to get hot, and the degree to which it gets hot depends on the amount of current we're passing through it or the amount of resistance of the medium. So I'm sure some of you guys stove in your apartment, your home, or whatever. Have you ever stopped to consider why the heating elements in an electric stove are shaped the way that they are? For those of you who aren't super aware of what I'm talking about, it's usually something like this, right? So you would have a lead that connects to the electronics of your stove top. And then it's this weird coil thing, like so. Can anybody tell me why they might be shaped this way?
Concentrates the heat.
So it increases the length of the heating element while keeping its area as small as possible. So if we coil it up like that, we get a very, very long length for our resistor, while the cross-sectional area is effectively constant, and the footprint on the stove stays effectively fixed. So some are smaller, some are larger because they're meant to handle different sizes of pots, but they all operate the exact same way. Okay, so they're coiled like that just to make them really long. How many of you guys own a space heater?
I have one.
I know, yeah, I know it's the middle of summer right now or the beginning of summer, so if any of you guys have a space heater, it's probably put up in storage. But when it comes time, when temperatures start getting cooler and all that kind of stuff, take a look at the heating element in your space heaters. All it is a section of what's called nichrome wire. It's a very, very thin wire, but it's very mechanically robust. And so effectively, you just take this wire that can handle very, very high heats. In fact, it'll start glowing red hot after you pass a relatively small amount of current through it. And they just wrap this wire all around willy-nilly inside of the heater. And then when you pass the current through that, it gets really, really hot. And then a fan is used to just blow that hot air off into your room. Again, it's just a simple application of resistance converting electrical energy into heat energy for a practical use, because once again, that is literally all a resistor can really do. Now, what do we as engineers use them for? It's usually to limit currents, right? So you guys, this is going to be kind of a side thing. In your engineering 120 class, probably on the first or second day of class, you developed a pretty simple circuit that looked something like this. You had 5 volts that was coming from a digital output pin of your Arduino. You had a resistor. By the way, this is the schematic symbol for a resistor. It's also the schematic symbol for a conductance for what it's worth. If I'm not mistaken, this was either a 220 ohm resistor or a 470 ohm resistor. And then you had an LED. The purpose of that resistor was just to limit the amount of current that was flowing through the LED, because the resistance of an LED is actually rather small. And because it's made of sensitive semiconductor materials, it burns out very, very easily if you apply too large of a voltage drop across it. So the resistor is used to just take some of that electrical energy that's supplied by that 5 source and convert it into heat, so that not all of the energy supplied by the source hits the LED and causes it to fry. So it's still doing the same thing, converting electrical energy into heat energy. We just view it a little bit differently because it's providing a practical use for us when designing electronics. Okay. All right, so I want to hit you guys with a couple of mathematical relationships here really quickly. So we have Ohm's law. Let me explicitly define things here really quickly. Okay. So if we have some resistance R, like so, and there is a voltage drop across our resistor, let's call it VR, positive polarity on the left, negative polarity on the right, and we have some current flowing through our resistor, which we'll call IR, then Ohm's law tells us that the voltage drop across the resistor, VR, is equal to the current flowing through the resistor times the resistor value itself. This is the Ohm's law that you guys are all familiar with. Just good old V is equal to I times R. Now, I'm going to throw a little hiccup into things here. And I'm going to draw a second resistor. And in this case, I'm going to put the negative polarity terminal on the left and the positive polarity terminal on the right. My current is now going to be flowing into the negative polarity terminal. So what do you guys think Ohm's law should look like now?
V equals negative IR.
Exactly right. So we have to include that negative sign there because that's what's going to force our resistance to be absorbing power. Because as I mentioned previously, resistors can literally never store or supply power or energy. All they can do is absorb energy. So anytime we have the current flowing into the positive polarity terminal of a resistor, Ohm's law gets a positive sign. Anytime we have the current flowing into the negative polarity terminal of a resistor, Ohm's law gets a minus sign. Okay. Now, for conductances, this works effectively the exact same way. So if we have some conductance G, like so, and we apply a voltage drop across the conductance positive polarity on the left, our current IG is flowing into the positive polarity terminal, then Ohm's law tells us that IG is equal to VG times G. So it's just this exact same thing as Ohm's law, except the current and voltage have switched roles. And whenever we have a conductance and the current is flowing into the negative polarity terminal, like so, Ohm's law will get a minus sign. Now, realistically, outside of today's lecture and a couple of homework assignments, actually probably just this one homework assignment and the in-class assignment associated with this lecture, we're not really going to see conductances a whole heck of a lot. So I would argue that instead of learning a separate set of equations and all of that kind of good stuff, your best bet whenever you're dealing with a conductance is simply to take the reciprocal of that conductance to convert it into a resistance and then just treat it like a resistor from there on out, okay? Or for those of you that are in electrical engineering, when you get to your electronics classes and things like that, as well as your classes dealing with transmission line theory, that's when you'll start to see conductances being used a whole heck of a lot. But for the lower level classes, if you treat every conductor as if it were a resistor, you're going to be perfectly fine. So that is very much what I would suggest all of you guys do for this class. All right, so let's look at something else really quickly related to these equations, okay? So power absorbed by a resistor. We know from our last class meeting that this should simply be the product of the voltage drop across the resistor and the current flowing through the resistor. Well, we can simply substitute in Ohm's law to express our voltage in terms of our current or our current in terms of our voltage. And so what we're going to find is that in terms of only voltage, the power absorbed by a resistor is the voltage drop across the resistor squared divided by the resistor value. And it can be expressed only in terms of the current as the current flowing through the resistor squared times the resistor value. We can develop a similar set of relationships, which again, I don't expect you guys to actually ever use for our conductance. So the power absorbed by a conductance is the voltage drop across the conductance multiplied by the current flowing through the conductance. And this is going to look like V squared times G or I squared divided by G. All right, we've spent about half an hour talking about Ohm's law. Does anybody have any questions about Ohm's law before we move on to our next circuital law? Before we move on, I just want to make a suggestion to you guys, just for your next couple of homework assignments and all of that kind of stuff. It might be in your best interest to have this information that I've boxed in right here handy in front of you whenever you're doing any of your circuit analysis, just to remind you that anytime you see a current flowing into the positive polarity terminal, give Ohm's law a plus sign, and anytime you see a current flowing into a negative polarity terminal, to give Ohm's law a minus sign. Just keep this nearby as a reference until that's kind of ingrained in you, because the overwhelming majority of mistakes that I see students make over these first few lectures are literally related to just whether or not there should be a minus sign. All right, so now I would like for us to talk about, let me just go to a fresh piece of paper here. Kirchhoff's voltage law. Thinking about doing new subtopics in blue. And commonly refer to this as KVL, okay? So Kirchhoff's voltage law says that the algebraic sum of all voltages around a closed loop must equal to 0 regardless of the path taken. Okay. So in our last class meeting, we learned that voltage is nothing more than the amount of work per unit charge required to move charge around a circuit. So voltage is inherently a measure of the amount of energy transferred in moving charge around. And so the sum of all of the voltages is the sum of the energy transferred in the system. So Kirchhoff's voltage law is really just the law of conservation of energy as applied to circuits, okay? It can never be violated. It must always be true. So what we are going to use Kirchhoff's voltage law to do is to determine unknown voltages in a system. And then if we introduce Ohm's law as well, we will be able to determine both unknown voltages and unknown currents. So let's see that put into action. Okay. So let's say that we have the following circuit. I've got a 10-volt source, positive polarity on top. I've got some arbitrary element A. I've got some arbitrary element B. And I'm going to put a 3-volt source over here on the right. Let's say that the voltage drop across element A is 5 volts, positive polarity on the left, and we want to determine the voltage drop across element B, and I'm going to choose for the positive polarity terminal to be on the right. So let's just call this VB, like so. So whenever I apply Kirchhoff's voltage law, I typically imagine a current flowing around a path, and I follow that current around in order to figure out what elements should get what signs and things like that. So I'm going to ask you guys a question. Would you rather follow a current that's flowing clockwise in this circuit or counterclockwise in this circuit? And it really doesn't matter which one you choose, just pick.
Clockwise.
Clockwise. Okay. So we're going to follow some current clockwise around the circuit, and I've indicated that with that orange arrow. So when I apply Kirchhoff's voltage law, I start at the bottom left-hand corner, and I just follow that imaginary current around until I get back to the same spot in the circuit, okay? So I'm just going to make a note here. Following the orange arrow. Starting at the bottom left-hand corner, the first thing I see is the 10-volt source. I see the negative polarity terminal first, so I'm going to put negative 10 volts. The next thing that I see is element A, and I know that the voltage drop across element A is 5 volts, so I'm going to put 5 volts here. Well, the first thing I see is the positive polarity terminal, so it's going to get a plus sign. The next voltage I see is going to be VB. I see the negative sign first as I follow that orange clockwise path. Then I see the 3-volt source. I see the negative sign or the negative polarity terminal first. And now I'm back down here at the bottom. And because we just have a wire, there is no voltage drop. So I'm back at the same node that I started from. So I'm just going to put this equal to 0. And so I can rearrange things a little bit here. So I'm going to move VB to the right-hand side of the equal sign. And so that's going to give me VB is equal to negative 10 volts plus 5 volts minus 3 volts, or VB is equal to negative 8 volts. So now, just for the sake of argument, let's see what would happen if we followed the current in the opposite direction. So if I were to follow the purple direction, what's the first thing that I see?
Positive 3 volts.
All right, so 3 volts, and I see the positive polarity terminal first, so it's going to get a plus sign. Absolutely correct. What do I see next?
Positive VB.
All right, absolutely correct. What do I see next?
Negative 5 volts.
Negative 5 volts. Thank you very much. And what do I see next?
Plus 10 volt.
Positive 10 volts. And I'm back to where I started from. So now, rearranging things a little bit, I'm going to leave it on the left-hand side. So when I move that 3 volts over, it's going to look like negative 3 volts. When I move that 5 volts, or excuse me, negative 5 volts over, it's going to look like positive 5 volts. When I move that 10 volts to the other side of the equal sign, I get minus 10. And therefore, VB is once again equal to negative 8 volts. So it really does not remotely matter what direction I choose to take when I'm applying my Kirchhoff's voltage law relationship. I'm going to get the same result either way. So how we choose to apply it is completely arbitrary. As long as we start and end at the same node, we're going to get the same result 100% of the time. All right, let's increase our level of difficulty here by giving you a little bit less information and also introducing a dependent source. So let's say that I have a 120 volt source, like so. Here's a 30 ohm resistor. Here is a dependent source. That's going to be twice VA, and I'll define what VA is in just a moment. Here is a 15 ohm resistor. And let's define the voltage VA to be the voltage drop across the 15 ohm resistor defined with the positive polarity on bottom. Okay. So here we're going to wind up applying Kirchhoff's voltage law as well as Ohm's law, with our ultimate goal being figuring out, let's figure out a couple of different things, okay? The first thing that I want us to figure out is what VA is. Let's put something a little weird here. I'm going to call this voltage VB. I want us to figure out what that is. And I want us to figure out the power supplied by the 120 volt source. I'm going to make a note here. And the power absorbed by our dependent source. So, do we want to apply KVL in a clockwise path or a counterclockwise path? Again, it's completely arbitrary.
Let's do clockwise again.
Clockwise, okay? So let me just make a note. So we're following our current in this direction, and I'm going to go ahead and give this current a name now. I'm just going to call it I, and we're going to have to wind up using that. And we'll see what that entails in just a moment, okay? So, starting at the bottom left-hand corner, what's the first thing that I see?
Negative 120 volts.
Negative 120 volts, okay? What do I see next?
30 ohm resistor.
So we see a 30 ohm resistor, okay? Now, we're applying Kirchhoff's voltage law, which means that our goal is to add up voltages, okay? Our 30 ohm resistor does not have a specified voltage drop over it, which means we are going to have to introduce one. Now, we're going to get to a point where we're going to do all of this. Right now, we're going to do this step by step in a very granular detail in order to make sure that everybody understands what's going on. But after you've practiced this for literally maybe a day or two, you'll start combining some of these steps together, okay? So I need to define a voltage drop across the 30 ohm resistor. So I'm going to call it, for lack of a better word, V30. I would like for you guys to choose whether I'm going to put the positive polarity terminal on the left or the positive polarity terminal on the right.
Positive on the left.
Positive on the left, okay? So now that I've defined V30 to have its positive polarity terminal on the left, I believe the next part of my KVL equation should just be plus V30. Are we all okay with that?
Yep.
All righty. So what's the next thing that I see?
Plus 2 VA.
Plus 2 VA, all right. And what's the next thing that I see?
Other resistor.
Right, so it's the 15 ohm resistor. However, the 15 ohm resistor has a specified voltage drop across it, VA, with a positive polarity terminal on the bottom, terminal on top. So I would call this, well, I see VA, and because I see the negative sign first, I'm going to call it minus VA. And now I've closed my loop, and I can set this equal to 0. We can rewrite this a little bit. So for example, we could move our constant term over to the right-hand side of the equal sign. So V30 is going to get left alone because it only shows up once. I have twice VA minus VA. So 2 minus 1 is just plus VA. And this is equal to positive 120 volts. Is everybody okay with the little amount of algebra that I did there?
Yep.
All right, so we have a little bit of a problem in as much as we have a single equation, but now we have two unknown quantities, V30 and VA. So in order to sort that out, we're going to wind up using Ohm's law. Ohm's law will allow us to express both of those voltages, V30 and VA, in terms of that current I that's circulating around the circuit. Okay. So let's make a note here. So here's where our Ohm's law equations are going to be. So I would like for you guys to tell me how we are going to express V30 in terms of the current I.
I times 30 ohms.
I times 30 ohms, absolutely right. So 30 ohms times I, okay. What about VA?
Do I times 15 ohms. Or negative
So
I times 15 ohms.
there we go, 15 ohms times I, and then we get a negative sign out front because that current I is flowing into the negative polarity terminal of VA. So if we substitute both of these relationships into this expression, we're going to wind up getting 30 ohms times I plus VA, so plus minus, so that's just going to look like minus 15 ohms times I is equal to 120 volts. And from this, I is just 120 volts divided by 30 ohms minus 15 ohms. So 120 over 15 is 8 amps. Are we okay with my algebra here? Nobody's saying they see a problem with it, so let's move along. Okay. So now let's start answering some of the questions that we were posed. Okay. So if we want to find VA, that's literally just negative 15 ohms times I, which we found to be 8 amps. So if I'm not mistaken, that is, let's see, 15 times 8 is 30 times 4 is 120. Excuse me, negative 120 volts. Now let's figure out VB. I'm going to modify this. So KVL around the outside loop is what that equation is. So if we wanted to find VB, we have two different paths that we could choose. This is something that tends to confuse you guys early on. So I'm going to try to do as best I can explaining things. But there's nothing that's preventing us from writing a Kirchhoff's voltage law equation around this loop, where I've just arbitrarily chosen to go in a clockwise direction, or around this loop, where once again I've arbitrarily chosen to go in a clockwise direction. I'm going to call this 1 and this one 2. So Kirchhoff's voltage law is just the sum of the voltage drops around any closed path. So as long as I start and end at the same node, it does not matter what path I choose, and it doesn't matter if there's current flowing through all or just a portion of the path that I choose, because I'm only concerned about the voltages, okay? So we can think of this voltage VB here as effectively what voltage we would see if we were trying to use a multimeter to measure the potential difference between those 2 points, which is all that a voltage is, okay? So do you guys want to write a KVL equation around path 1 or path 2?
1.
Path 1, okay? So let's come down here. KVL around path 1. So the first thing that I see is the 120 volt source, and I see the negative polarity terminal first. So I'm going to do negative 120 volts. The next thing that I see is that voltage drop V30, because I've already defined it in terms of that current I. I'm just going to put plus 30 ohms times I here. Sorry, shouldn't be a 1. And the next thing I see is the voltage drop VB, and I see the positive polarity terminal first. So I'm just going to have plus VB is equal to 0. So even though there's not any current flowing through the middle of this circuit, because I've defined a voltage there as a potential difference between those 2 points, it can be part of a KVL equation. If I rearrange this, I'll have VB is equal to 120 volts minus 30 ohms times I, where I is 8 amps, and that's going to be 120 volts minus 240 volts comes out to be negative 120 volts. Does anybody have any questions, comments, or concerns about how we solved for VB? I understand that this is probably a little odd, but it is something that we're going to wind up doing very often. All right, so unless I'm told otherwise, I'm just going to take your silence for, I get it, move along, old man. The power supplied by the 120 volt source. So let's put that over here on the right. So because we're dealing with the power supplied by a voltage source, our only thing that we can do is use our relationship that P is equal to voltage times current. So what's the voltage drop across the 120 volt source?
Is it 120?
120 volt.
It's 120 volts. That's why it's a 120 volt source. It provides a fixed amount of voltage. Okay, so 120 volts. How much current is flowing through the 120 volt source?
The 8 amps.
8 amps. All right. We are calculating supplied power. So is that current of 8 amps flowing into the positive polarity terminal or into the negative polarity terminal of our 120 volt source?
Into the negative.
So it's flowing into the negative, and we're calculating supplied power, which means we don't need to worry about changing the sign here. So we're just going to have 120 times 8, or 960 watts. Okay. Now let's worry about our dependent source. Okay. So what's the voltage drop across our dependent source?
$240 volts.
Positive
Negative.
or negative? Negative 240 volts. So the voltage drop across our dependent source is twice VA. So I'm going to put a 2 out here. And then VA is negative 120 volts. So that will be negative 240. What's the current flowing through our dependent source?
Still 8 amps.
8 amps. All right. And the current is flowing into the positive or negative polarity terminal of our dependent source.
Positive.
All right. Because we're calculating absorbed power for our dependent source, we do not need to change the sign. Okay. So this should be negative 1,920 watts. So what does it mean that that value is negative? Well, the dependent source is actually supplying power as well. That's all it means. Okay. So we've learned what Ohm's law is, excuse me, not Ohm's law, Kirchhoff's voltage law is. We've looked at a couple of different problems that uses it. One last thing before we move on here. So let's say that I have this circuit. So here's a 10 volt source. Here is an 8 ohm resistor. Here is a 6 ohm resistor. And I'm interested in finding the voltage drop across the 8 ohm resistor, positive polarity on top. So I'm going to call this V8. And I'm interested in finding the voltage drop across the 6 ohm resistor, positive polarity on bottom, which I'm going to call V6. Okay. If I were to write a Kirchhoff's voltage law equation for this circuit, what would I wind up seeing that V8 is?
The 8 ohms times I.
So let's define a path here. Okay, so I really only have two options for a path that involves that voltage V8. I could do this path, arbitrarily choosing a clockwise direction, or I could do this path, once again, arbitrarily choosing a clockwise direction, right? So let's look at what happens when I do KVL at path 1. Starting at the bottom left-hand corner, I would have negative 10 volts plus V8 is equal to 0. And rearranging this then, I would get V8 is equal to 10 volts. If I wrote the KVL relationship around path 2, I would see that negative V8 minus V6 is equal to 0. And therefore, negative V6 is equal to positive V8. So that tells us what V6 is. So what's V6 going to have to be?
Negative 10.
Negative 10 volts, okay? So I got a little nervous there when somebody mentioned the current, because we can find currents here, but that's not really what's important. Let me erase these two. Actually, I'll leave those two paths there, just for the sake of argument. How are all of these elements connected to each other?
Parallel.
They're all in parallel, right? We can see that very easily by identifying our nodes. So I have this top node here that I'm doing in pink. And I have this bottom node here that I'm going to do in this dark green color. And we can see that all of these elements share the pink node on top and the green node on bottom. They're all in parallel. So what we just found out is that Kirchhoff's voltage law tells us that all of the elements that are connected in parallel have to have the same voltage drop over them. The only reason that V6 is negative 10 volts instead of positive 10 volts is because it's of the opposite polarity. So all of the magnitudes have to be the same. And if we have a change in polarity, we just change the sign, just like we discussed in our last class meeting. Okay? So I'm sure that you guys have heard before that things connected in parallel have the same voltage drop across them. The reason for that is Kirchhoff's voltage law. So I just wanted to show you guys where that comes from. All right. Any other questions or comments about Kirchhoff's voltage law before we move along to Kirchhoff's current law? All righty. Okay, so Kirchhoff's current law. Kirchhoff's current law states that the algebraic sum of all currents entering or exiting a node must equal to 0. This might be slightly different than what you guys were taught in your other courses. So we're going to talk about all of that in a moment. But before we do that, I want us to think about what this means contextually, okay? So in our last class meeting, we learned that current is nothing more than the rate at which charges pass a given point in a circuit, okay? So pass a particular node, pass through a certain circuit element, it's all the same to me, okay? So Kirchhoff's current law states that the sum of all of the currents entering a node must equal to 0. So effectively, Kirchhoff's current law is the law of conservation of charge as applied to circuits. Because if all of the currents entering a node didn't equal to 0, then that would mean that charge is being either created or destroyed somewhere within our circuit, which literally cannot be true. Okay. So now let's look at something here really quickly. So I'm going to draw a node point here on the page, and I'm just going to give myself a couple of different paths. And I'm going to arbitrarily draw currents. And some are going to be flowing into the node, and some are going to be flowing out of the node, right? So let's say this is going to be our current I1, and it's flowing in. This will be our current I2, it's flowing out. This will be I3, it's flowing out. I4 will be flowing in. And I5 will be flowing out. Okay. Over here, I'm going to put KCL number 1. Okay. Currents flowing in is equal to 0. So we are literally just going to apply Kirchhoff's current law as I've written its definition up top. Okay. So a current I1 is flowing into the node. A current I4 is flowing into the node. So do I just put equals 0 here? Because the law says the algebraic sum of all of the currents entering a node must equal to 0. Well, unfortunately, it's not that simple. Okay? So instead, I have to think about, well, if I have 5 paths coming off of this node, I should have 5 terms in my Kirchhoff's current law equation. So a current I2 is seen exiting the node. And we know that in order to change the direction of a current, we simply multiply the current by a factor of -1. So if I2 is exiting, negative I2 is entering. So we have to take account negative I2 is entering the node. Well, negative I3 is also entering the node. and negative I5 is also entering the node, and all of these added together equal to 0. Now let's look at KCL number 2, okay, where I'm going to say that currents exiting or currents flowing out, sorry, equal to 0. Okay. So if I1 is flowing in, then negative I1 is flowing out, positive I2 is flowing out, positive I3 is flowing out, negative I4 is flowing out, positive I5 is flowing out, and these must all equal to 0. Mathematically, what we have here is the exact same thing as what we have here, except it's multiplied by a factor of -1 because our reference direction is different. That's the only difference between these two relationships, okay? So they are literally the exact same thing and give us the exact same results. The last way that we can think about Kirchhoff's current law is actually the way that you guys are probably used to. And that is the sum of the currents flowing in is equal to the sum of the currents flowing out. So we know that I1 and I4 are flowing in, and we know that I2, I3, and I5 are flowing out. So that's what our KCL equation would look like. And this equation is literally nothing more than this equation right here, except all of these terms, I2, I3, and I5, move to the other side of the equal sign. So once again, it's the exact same relationship. It's just looking at it from a slightly different perspective. Okay. So for you guys, right now, you're probably most comfortable with using this relationship. Sum of the currents flowing in is equal to the sum of the currents flowing out. If I'm not mistaken, that's what you're taught in the Engineering 120 series. Okay? There is nothing remotely wrong with this representation, and I still use it regularly. However, it is not the one that I use most often. I take this second representation. The currents flowing out of a node is equal to 0. And the reason why I use this representation is because when we apply a technique called nodal analysis that we're going to learn about next week, using this particular representation of Kirchhoff's current law gives us the correct results with the minimum number of extra negative signs. And I know that I personally tend to make a lot of mistakes when I have too many negative signs floating about. So that's the one that I used most often. But whatever one makes you the most comfortable is the one that you should be using. So let's work a couple of examples here. So let's start with something fairly straightforward. Let's say that we have an 8 amp source. An arbitrary element A like so, that has 1 amps of current flowing down. A 2 amp current source direction down, and then element B over here on the right. And let's define the current IB as flowing up. So if we're going to apply Kirchhoff's current law, we need to decide whether we're going to apply it at the top node or the bottom node. And then we need to decide whether we're going to apply formulation number 1, number 2, or number 3. So somebody call out top or bottom node.
Top.
So KCL at top node. And then I think that was Baylor talking. So Baylor, you get to volunteer which version of KCL we're going to apply here. So number 1, number 3. Okay, so KCL number 3. So that means that all of the currents that are flowing into the top node has to be equal to all of the currents that are flowing out of the top node. All right. So 8 amps of current is flowing into the top node. The 1 amps is flowing out. 2 amps is flowing out. IB is flowing in. So I believe this is what our KCL equation should look like, applied at the top node using currents flowing in equals currents flowing out version of KCL. Okay. We can rearrange this very easily and see that IB is 1 amp plus 2 amps minus 8 amps is negative 5 amps. If we used either of the different formulations or either of the other formulations or applied KCL at the bottom node, we would get the same exact result. So once again, it does not matter which method we choose here, we're always going to get the exact same result. So whatever you're most comfortable with should be the method that you use. Let's look at another example. So I've got a 5 amp source here. A 10 ohm resistor here. One amp source flowing down. Let's put a 8 ohm resistor here. And let's put a 6 amp source up here. And I want us to find, so let's say I want the current flowing through the 8 ohm resistor. I want the voltage drop across the 10 ohm resistor and while we're at it, let's find the power absorbed by the 5 amp source. All right. So whenever I have a circuit like this, where all of the elements are connected in parallel, this should be a very good indication that you're supposed to be applying Kirchhoff's current law to this circuit. So that's what we're going to do here. Do we want to apply KCL at the top node or the bottom node?
Top node.
Top node, all right. And You guys pick which version of KCL we're going to apply, but let's not use the currents flowing in equals currents flowing out. Let's see another one in action.
Number
So-
2.
Number 2, so that's all of the currents exiting. All right. So that 5 amp source on the left, it is entering the top node, so it should get a negative sign. We weren't explicitly given a direction for the current flowing through the 10 ohm resistor, so we're going to have to make one up. So do you guys want to define that current as flowing up or down?
Down.
Down, okay. So this will be our current I10 flowing down. Since it is flowing down, it is exiting the top node, so we are going to give it a positive sign. The 1 amp source is exiting the top node, so it's going to get a positive sign. The current I8 is exiting the top node, so it'll get a positive sign. And lastly, the current of 6 amps is entering the top node, so it'll get a minus sign. So we could rearrange this a little bit, and we would find that I10 plus I8 is equal to 5 plus 6 minus 1 is equal to 10 amps. Hope you guys are all okay with my algebra and mental math there. So once again, we're in a situation where we have 2 unknown quantities, but a single equation. So in this case, we're going to relate everything to that voltage V10, okay? Now, what did we learn at the end of our discussion on Kirchhoff's voltage law? Whenever we have things connected in parallel, they have the same voltage drop over them, okay? So even though I defined that voltage V10 as the drop over the 10 ohm resistor, that exact same voltage V10 with the exact same polarity occurs over the 8 ohm resistor because the 10 ohm resistor and the 8 ohm resistor are in parallel. So we can use this to write our Ohm's law relationships. So use Ohm's law and tell me what I10 is in terms of V10.
V10 over 10 ohms.
So V10 over 10 ohms. And should that get a positive sign or a negative sign?
Positive.
Positive, because the current's flowing into the positive polarity terminal. Absolutely correct. Now let's look at what's going on with that current I8. Somebody else tell me how to put that in terms of V10.
V10 divided by 8 ohms.
V10 over 8 ohms, absolutely correct. And it should get a positive sign because the current I8 is flowing into the positive polarity terminal. So now we'll substitute both of these relationships into our KCL equation. So that's going to give us V10 over 10 ohms plus V10 over 8 ohms is equal to 10 amps. And we can solve that for V10, which I can't do this one in my head, so let me throw it in a calculator real quickly. So x over 10 plus x over 8 is equal to 10. Solve for x. Calculator's thinking about it. So I got 44.444 or 400 over 9 volts. So we've solved for V10. I8 is just V10 over 8 ohms. Or 50 over 9 amps. And lastly, we want the power absorbed by our 5 amp source. So what's the voltage drop across our 5 amp source?
$400/9.
Yep. Since everything is in parallel, that's the only voltage in our whole system. What's the current flowing through our 5 amp source?
Five amps.
5 amps, absolutely right. Is this current flowing into the positive polarity terminal or the negative polarity terminal? So this can be a little bit tricky. So I'm going to do what I did for the 8 ohm resistor. So V10 is defined as negative polarity terminal on bottom, positive polarity terminal on top. So I'm explicitly putting that voltage as the voltage drop across my current source to see whether that current is flowing into the negative or into the positive. In this case, it looks to me like the current is flowing into the negative polarity terminal, which means we will need a negative sign in order to get our absorbed power. And this to me comes out to be 2000 over 9 with a negative out in front watts. All right. Does anybody have any questions on Kirchhoff's current law? And actually, there's one last thing I want to talk about really quickly, so hold on to your question for just a moment, if you don't mind. So let's say that we had a circuit like this, where we have a 3 amp source, and then a 5 ohm resistor. That omega looks terrible, pardon me. And then a 2 ohm resistor over here. I'm going to define this as the current flowing through the 5 ohm resistor, so let's call it I5. And I'm going to define this as the current flowing through the 2 ohm resistor, so let's call it I2. Okay. So if I apply KCL at my red node, I can see that I have 3 amps flowing in and I5 flowing out, and using the KCL is sum of the currents flowing in is equal to sum of currents flowing out. I can see very easily that I5 is just 3 amps. Now, if I apply KCL at this blue node, I can see that I have I5 flowing in and I2 flowing out. So I5 must be equal to I2, which means this is also equal to 3 amps. So how are the 5 ohm resistor and the 3 amp source connected to each other?
In series.
And how are the 5 ohm resistor and the 2 ohm resistor connected to each other?
Just in series.
They're in series as well. So we can say that whenever things are connected in series, they have the same amount of current flowing through them. And that allows us to say that in this case, all 3 of these are connected in series because they all share the exact same current flowing through it. So we've slightly, modified our definition for a series connection now to be whenever elements have the same current flowing through them, we consider them to be connected in series. Okay, now does anybody have any questions about Kirchhoff's current law? Alrighty, so let's look at in-class assignment number 2. So we are asked to determine the voltage drop over the resistor and the conductance and the power absorbed by these elements in the circuit below. Now, I did not specify the polarity for the voltages, so I'm going to go ahead and do that now. So let's do positive polarity on the left for the 5 ohm resistor. So this will be VR. And we'll do positive polarity on top for the conductance. So this will be VG. So using Ohm's law, V is equal to I times R. So the voltage drop across our resistor is going to be 6 amps because 6 amps of current is flowing through all of these series connected elements. We just found that out a moment ago. The resistor value is 5 ohms. And so 6 amps times 5 ohms gives us 30 volts. Easy enough. The power absorbed by our resistor can be found either by doing V squared over R or I squared times R. So let's do the I squared times R thing. So PR is going to look like 6 amps squared times 5 ohms. So 36 times 5 is 150 plus 30 is 180 watts. For our conductance, we know that VG should be, so let's see if it's I times R, it's I times 1 over G. So I over G, so 6 amps divided by 0.25 Siemens, which is the same as 6 times 4, or 24 volts. For our conductance, that's going to look like V squared G or I squared over G. So PG would be 6 amps squared divided by 0.25 Siemens. So 36 divided by 0.25 gives me 144 watts. Just as a very quick aside, how much power does the 6 amp source have to be supplying?
$180 watts.
I disagree. So Telegen's theorem tells us that the sum of the powers absorbed has to be equal to the sum of the power supplied. So I think it's 180 plus 144, which to me is 324 watts. We could also have applied Kirchhoff's voltage law to find the voltage drop across the 6-amp source, which would just be nothing more than VR plus VG, according to Kirchhoff's voltage law. So that would have been 54 volts times 6 amps. Comes out to be 324 as well. So one of the great things, and also the things that annoys you guys the most, is that there's always more than one way to do stuff in circuit analysis. All right, so we went over that one pretty quickly. If anybody has any questions, I would be happy to answer them. If not, we can move along to problem number 2.
Can you just scroll back up just a little bit for a second, up to the problem question?
Sure.
Okay, thank you. I just missed a little part of it.
No problem.
I got it. Thank you.
All righty, let's move along to problem number 2. Okay. So for this circuit, we are supposed to use Kirchhoff's current law, or excuse me, Kirchhoff's voltage law to determine the unknown voltages Vx and Vy. So this is another one of those where we have this weird voltage of 12 volts just kind of in the middle of the circuit. So I want to explicitly explain what it means. So if I identify my nodes, so I have this node up here on the top that I've just done in red. And then I have this node here in the middle that I've just done in green. There is a 12 volt difference in electric potential between the red node and the green node. That's all that 12 volt thing means there. Okay? So the key to answering a question like this is finding a closed path that contains the unknown that we want and making sure that it's the only unknown quantity in our path. So I'm going to identify several different paths here. So this is a closed path. However, it's not a good closed path for us to use because it contains the unknown voltage Vx. It also contains the unknown voltage Vy, and it contains a voltage drop across a resistor right here where we don't know anything about this resistor at all. We don't know the current, we don't know the voltage, and we don't know the resistor value. So this would be a terrible path to use to try to solve this question. Instead, we might use a path like this. Now, the voltage Vx is the only unknown quantity, right? So if we start at the bottom left-hand corner and work our way around in a clockwise path, sorry, KVL at pink path, what would we wind up getting? Somebody help me out, please.
Yeah, negative Vx
Negative
plus 12
Vx
volts
plus 12 volts
minus 6 volts
minus
equals 0.
6 volts is equal to 0. So we can rearrange that really quickly to say that Vx is equal to 12 minus 6 is 6 volts. Easy peasy. I would like for you guys to try to find a path that we could use to find Vy. You're going to have to, I guess, describe it to me so that I can draw it.
Could we go VY to 4V to 6V to 12V?
So I believe you were describing,
Yes, sir.
this path, okay? So let's start here, just because that's where I started drawing the line. So KVL at orange path. So what would that KVL expression look like?
VY,
Positive VY.
yeah, plus 4V.
All right.
Minus 6V. Minus 12V.
Equal to 0, okay? And so we can rearrange that really quickly. So 12 plus 6 minus 4, so 18 minus 4 is 14 volts. And there we go. So when we're applying Kirchhoff's voltage law to find an unknown voltage, like we did in both of these examples, we want to make sure that the path we choose contains an appropriate amount of information that actually is beneficial to us. All right, for the last problem here, this one is going to take a couple of minutes, so I hope you guys will indulge me. Class is going to run maybe 3 minutes long, but it'll be okay. So we are specifically asked to use Kirchhoff's current law and Ohm's law to determine the unknown quantities, okay? So we're going to start with a KCL equation. And I'm going to say that we're going to do the top node because that's what we've been doing, and that's as good of a node as any. I don't believe we've used KCL number 1 before, so let's do that one. So that is currents that are entering the top node are positive, currents that are exiting the top node are negative. So I believe that the current IX is entering the top node. So let me be clear here. We have IX flowing up through that 6 kilo ohm resistor before it curves off to the right. So I'm calling it as entering the top node. So I'm going to have IX. I have a current of 6 milliamps that is entering the top node. So it's going to get a positive sign. I have a current of 4IX exiting the top node. So it's going to get a minus sign. Now I have this 2 kilo ohm resistor. There is no current associated with it right now, so we have to make a decision. Do we want the current flowing through the 2 kilo ohm resistor to flow up and enter the top node, or do we want it to flow down and exit the top node? Sorry, I don't know what the heck I just did.
And I make it flow down.
Make it flow down. All right, so I'm going to call this I2K. Since it is flowing down, it's going to get a negative sign. We have 2 milliamps flowing down, so that'll get a negative sign. And then we have the current IY, and it flows down and out of the top node. So it will also get a negative sign. Are we all okay with this KCL equation?
Yep.
All right. So now we're going to apply Ohm's law. Okay. So all of these elements are connected in parallel. So that means the voltage Vx is also the voltage drop across that 2 kilo ohm resistor, and it is also the voltage drop across the 3 kilo ohm resistor. So how am I going to express Ix in terms of Vx.
Do V6 or VX divided by 6 kilo ohm.
So Vx over 6 kilo ohms, should that get a positive sign or a negative sign?
Negative.
A negative sign, because the current Ix is flowing into the negative polarity terminal. Absolutely right. Now let's work on I2K. So how do I express the current flowing through the 2 kilo ohm resistor in terms of the voltage Vx?
Do a positive VX divided by 2 kilo ohm.
Absolutely right. And lastly, IY over there on the right flowing through the 3 kilo ohm resistor.
Positive Vx over the 3 kilo ohms.
Absolutely correct. And now we're going to substitute those three relationships into our KCL equation, which I'm going to do down here, right? So Ix, so that's negative Vx over 6 kilo ohms plus 6 milliamps minus 4 Vx over 6 kilo ohms. But because I have minus and another minus sign, that one's going to turn positive. Then I'm going to have minus Vx over 2 kilo ohms minus 2 milliamps minus Vx over 3 kilo ohms is equal to 0. And now I have one equation, one unknown. So I'm going to put this into the equation solver in my calculator. So negative x over 6,000 plus 0.006 plus 4x over 6,000 minus x over 2,000 minus 0.002 minus x over 3,000. Oh, my calculator ran out of memory, so I'm going to have to lump some things together here really quickly. So let me just do that here. So I have minus Vx over 6k plus 4Vx over 6k. So that's going to look like 3Vx over 6 kilo ohms minus Vx over 2 kilo ohms minus Vx over 3 kilo ohms is equal to negative 4 milliamps, if I did my algebra there correctly. All right, so solving this, I get Vx is equal to 12 volts, and then Ix would be negative Vx over 6 kilo ohms. So 12 volts over 6 kilo ohms is going to be 2 milliamps and the negative sign. And then lastly, Iy is positive Vx over 3 kilo ohms. So 12 over 3,000 is going to give me positive 4 milliamps. There we go. All right, I apologize for class running an extra 5 minutes. Hopefully you guys found some value in me working out the problems and all that kind of jazz. Once again, if you have any questions about anything, please feel free to email me, or you can ask questions at the beginning of our next class meeting. See you guys on Wednesday.